let's go back to the second part of today's session. So I'm going to close these windows. Okay, we don't need them. Okay, and I will close this one as well. So once again, you can find more details on how to get the results by watching the guest lecture videos, either from this semester or the last semester, because it's repeated. Oh, wait a second. Let me show you actually where you can find that. You go to YouTube. Okay, so it's this channel, and if you go to the videos, you will find that this one for the same example I did earlier. That's the this week tutorial of the 1 hour because we had a technical issue. We couldn't start at the time, so the time was just 1 hour. For more details, you can go to the last year recordings. So these are the last year recording. This is the session 1 and that's the session 2, where you can find more information, actually more detailed information about the work. These are not yours. It's about the pendulum and the slider crank, but you can use this one. I don't want to share the files with you because they were made for Western Sydney Uni, so I cannot share it. It's illegal. As I cannot share your files with them. So again, we're going to go to the mini project and we're going to go for the fourth task, which is going to be the virtual lab of the block and the spring system. Now, I don't know if you learned that already, but you know what the terms of the degrees of freedom is? What the term mechanical degrees of freedom or the motion degree of freedom? Exactly. So we have different mechanisms that are going to have different degrees of freedom. So if we're going to analyze the scenario we have here for the slope, have a current, at the bottom we have a spring and mass and damper. What will be the degrees of freedom we have here? How many degrees of freedom we have for the system? It's going to be nice actually to search for the term degrees of freedom for the mechanism, and this will give you a calculation step for the degrees of freedom. But here let's talk about the thing in general. If I'm going to put my hand over this chair and try to press it down, so I move in one direction, what's happening that the plasticity of the elasticity of the chair trying to absorb the force I put with my hand. So this will be 1 degree of freedom. We're only moving downward and upward. Same thing is happening for the green block with the spring and the damper. Like the motorcycle, when you see actually the spring and the damper, when you press it down the wheel without moving, this will be 1 degree of freedom. Now the current is also moving horizontally. This will be a 2nd degree of freedom because 1 degree plus 1 degree is going to be 2 degrees of freedom. This analysis is mainly going to be about the scenario we're going to have here. What's happening if I'm going to release this carrot downward? It's going to hit the green block. The green block will transfer the impact to the spring, which have something called the K value, which is the spring resistance. Sometimes they call it the spring constant. And we have the C value, which is the damping effect in the Newton second per meter. So it will depend on the velocity we're going to have for the carrot. Now, how we can increase the force created by this carrot? What are the options or the parameters to increase the force of the impact for this carrot? Have you played with these cards when you were a kid? How to make the things go faster? What you were doing? Increase the slope. 1. Second, increase the distance. Third, increase the mass. So these are the main 3 parameters. You can increase the velocity, the velocity for the part the red part, and also it's going to increase the force that you think the block C. Now, how to increase the absorption of the force by this system? The mass of the green block, the coefficient of friction, the spring constant, and the damping constant. So that's why you can see that in the motorcycle, we're going to have a small spring, and we're going to have a small shock absorber. In the car is going to be bigger, in the truck is going to be bigger. And sometimes in the trucks, they don't have actually the spring, they're using the leaf spring. You know what the leaf spring is. How many here don't know the term leaf spring? Put your hands up. Oh, good, everybody knows it. Girls, do you know what the term leaf spring is? Leaf spring? Well, don't worry, I can explain that to you. So usually in the heavy load, we don't use the normal spring, like the one that have this spiral thing. They use something called the leaf spring. Okay, which look like that. I don't know if you saw something similar to that in the trucks. So the leaf spring is going to be consist of multiple layers of the metal leaves connected together. So it will depend on the elasticity of these leaves. Okay, this can take more load, and actually till the 50s, most of the cars, the normal cars, were using a leaf spring as well. Most of the pickups nowadays using the leaf in the back and the normal spring in the front. Okay, so technology is not new, of course, and still in action because it is effective. We have the other way to do the absorption like the spring. We have something called the torsion bar. I don't know if you ever heard about that. Once again, is very popular, torsion bars. So I think that you've done last semester with us when Terry gave you the example of the torsion bar. So once again, it's going to depend on the twisting of the bar to absorb the load. So there's actually no spring. The torsion bar would do the work in addition to the shock absorber. The French car actually are very popular with this stuff. Sometimes they can be added the same thing to the front wheel in addition to the spring and the dampers. Okay, like what we have in this scenario here. Oh no, this is just a torsion bar. So this replacement for the spring, we're going to depend on the torsion we're going to have and the reflection back to absorb the shock. Okay, now let's go back to the example we have here. That's what was the virtual lab 2. Once again, you're going to download this one and unzip it, and you will find something very important. Okay, you will find something very important when you download this file, that it does contain some videos. And we will going to have a brief look about that. So actually, that's the one that I downloaded last week and unzip it. Okay, so if you're going to go to here, you'll find that we have 2 videos here. That's the first video, which is the introduction.
Hello, and welcome to this session. In this first video, I'd like to do a really quick introduction.
So he's going to take you through the things, explain to you the parameters to be changed,
see the MATLAB
explain to you the MATLAB model.
Don't see any wheels in this sort of model. That's because what we're going to do is use a prismatic joint.
Stop that.
The very first prismatic joint I'm clicking on now, the blue block. And that prismatic joint constrains the red part.
Here you have to build the Simulink model by yourself. You don't have experience with that, so they reduce the work to be just completing the connections. But I bring some of the models just to introduce you on how to do the work. You don't have to actually be brilliant with the MATLAB to do the work, because the second video is going to show you how to do it. So the second video is how to build the data logging.
In this video, I'm going to walk you through the process of creating the Simulink subsystem that allows you to sense and measure the task.
So it will show you how to fill these two
Okay.
boxes.
Editor to have about.
And actually there is a
Left
completed one.
And
So
so,
you
the way that you
just
make
have to
sure that
bring
this
the
works,
blo-
you want
the
to
blocks,
put your mouse over
how to
frame
put the measurement.
and this will give us the.
Okay.
And this
So
is where
just follow
we
these
need to
steps
type in the
and you'll
name,
find
the
out your
name.
way. So these are the videos. Now we go back to the MATLAB. Now I'm going to close these things because I don't need them anymore. It may ask me about saving anything. I don't want to save anything unless we're going to make a copy. So don't save anything. You can simply have two copies. One is going to be yours to change the parameter as much as you can. The other one, save the actual one. Actually, the zip file is going to be the original one. So just keep it as a spare in case if you missed out with the things, just delete everything and get the new file and start to do the work. Now, again, I want to clear the workspace. So I'm going to put the clear here. And I'm going to clear the command window by doing CLC. Okay, then I'm going to go back once again to the OneDrive, the MATLAB, sorry, drive, and look for the example of the impulse and the momentum virtual lab. Again, you can see that we have the task or the MATLAB, which is start here. Right click, open, and we're going to have this scenario. So you can see here, we're going to have the three different tasks. Task number one is define the numeric value for our system. Second is you will create the Simulink model for the system and simulate its dynamics. And third one is going to be you will analyze the data logged from the part one simulation and use it to confirm the principle of the impulse and the momentum PIM. For each task, you have to open the corresponding MATLAB script and follow the instruction inside it. So this will be task number one. What are the parameters we have for the momentum impulse? So I mentioned that the mass, the length, the angle, the spring constant, the Dunbar constant, the friction if we have any, and so on. So after we change that, we're simply going to run it. I'm not going to run anything right now. I'm going to check first the defining all the parameters. So the angle now is at maximum of 15 degrees. I will make it 13 degrees. You can see that this one has been updated. The parameter L2, I will take it to 1.7. The maximum is 2 meters. And for the L1, L4, L3, LZ, LY, you can change them as well simply by changing the value here. That's the mass for the inertia, and you can change the K value from here. The parameter K is the spring stiffness or constant, and this is the parameter M, which is going to be the C value, the density. Parameter K, which is how many Newton per meter we're going to have for the spring. And that's the data sample logger data sampling intervals in seconds, the environmental variables like the G value. And now we have everything to be ready for you. Okay, so you can see that this one is already operated. I'm going to run it very soon by clicking on this one. Now it did some of the calculations. And now we're going to go to the next step, which is explore all the model impulse momentum for the instruction, how to do that. Okay, to make a Simulink model for your work. Now, by the way, I would like to check if I already have these values to be changed, so I can write down something like the W, H, or S. And this will tell me that, okay, now we have these things already been verified. Okay, so again, I will do the run and see what will happen. Actually, not too many things changed. We should get some results to be sure here. Anyway, let's do the task number 2 and come back to this one later. Task 2 is creating the Simulink model. Okay, so this will open this file. Now we have these things have been generated. We can simply refresh that by repeat the process once again. Step number 1 is watch the introduction video that we watched earlier. Step number 2 is the implement of the subsystem for the measuring and logging times series data, and this will be done by checking the second video. Okay, and you can open the partially completed model for the impulse moment to do that. So you can see in this model, you are going to go for the sensors and the data logger from here. You need to complete these 2 parts. The video actually show you how to do that. And I advise you once again to start working on that as soon as you can. Just in case if you have any problem, you will tell me and I will be happy to check with the person who made the work and ask him what's the problem we have. Usually this will be the results box, the position and the velocity and the force we're going to have in Newton. After you make this one and make it run, and you would like to check if your answers are correct, you will go back and you can open another file, which is going to be the completed one. I'm going to go through this one very, very fast. Okay, now in case of the emergency, you can get the final model impulse Simulink model. That's a completed one. If you failed actually to do the work, you can see that this sensor and the data logger has been already been completed, and it will give you the result directly by press run. Okay, and it's going to show you actually the process. So you can see what's happened to the box is slowing down, and the distance will be start to reduce because simply the dynamic system here is absorbing the energy until the energy will go to 0. So it's something like, I think that most of you had anyone here play squash or something like that? Yeah, so when you hit the wall, the ball not going to come back to you with the same speed because certain amount of the energy has been absorbed by the wall. If the wall actually is going to be moving, this will absorb more energy. If you're going to hit the ball between 2 walls next to each other, and that's actually one of the examples that you can see most of the time, that the thing will start to hit the walls and then start to slow down until it's going to be stopped. So now let's see how this result is going to be translated to us as a graph. So once again, you are going to just simply double click on this block, and these are the results, which is going to be more clear if you're going to see it like that. So what you can see here that the initial position is considered to be the initial point 0. We're going to drop the carrot for 1.7 meters. It's going to hit the green block. This green block going to absorb amount of the energy and send back the carrot to only the distance of 0.6, negative 0.6. So from the 0 to negative 0.6, drop down to 0, to negative 1.5, will go to -1, and keep slowing down until it's going to be steady at 0. For the velocity, 0, go to the maximum when it's going to hit the block. Then it's going to be reverse back to 2, reverse back to 2.1, and just keep it going forward and backward. Now you'll say, okay, now why this one is 2.1 and this one is 2.1 as well? Why this one is going to be 1.8, this one 1.8? Because when you're going to push it back, it will initiate a new velocity because the distance has been pushed to. Later here, we're going to slow down until it's going to reach the 0. For the forces, the first impact is going to be the highest, the last impact is going to be the lowest, and then we're going to have the static to be 0. Because once again, we said that the distance is going to decide what will be the impact force we're going to achieve. I think that we have other stuff to be shown here. Just let me check the model again. Okay, so once again, that's the only thing you have to do. Just change the parameters and run the process once again. It's going to be a nice idea to have 3 or 4 sets of the data and run them all together and find out. Yeah, so you can see that's experiment number 1, that's 2, and that's 3. You just change the data and get the results. Again, it doesn't have to be the same data we have here. Make your own, okay? Make your own sets and run them and see what will be the answer. Now, the task number 3 is going to be the analysis of the impulse momentum, and this will be mainly about a MATLAB simulation, I think. We don't need to change that. I don't need to change this one. Okay, so once again, yeah, this will be about the time interference. So here we can change the time parameters from here. Time to start and time to stop. And by run it, I'm going to update these values. Okay, so the force threshold also has been given here. And by changing these parameters using this equation, we should have a new result to be updated at this point. Okay, so that's the code. I'm going to run this section here. Okay, and you will find out that these figures actually has been updated and the tables also has been updated. If I get to run it in general, by the way, one of the things that I advise you to avoid is don't click on the line and then run it. You will see what happened is here we're going to have the debugger. Don't do that. Okay, so I'm going to close that by simply untick it. Anyways, I'm going to stop this one and I'm going to run the whole code. And now you can see that the time is changing. The position is changing. The velocity. Why is not updating the force? I don't know why it doesn't update the force, but the force also should be changing. Okay, so these are similar to the graph that we saw earlier, and you can once again change the time and try to do the work. So this will be a practice session. Just to compute the area under the curve to find these parameters. That's the equation given to you already. Okay, and it's about the, you remember this equation, right? We did last week, the impulse, resolve the impulse and the momentum. Okay, and that's it. Yeah, well, actually, I don't want to go too much with that. It should be clear. I hope that the velocity has been changed now. Sorry, the force. No, that's strange. Anyways, yeah, I don't want to go too much with this one because, as I told you, the most important task for me is that you now don't scare about how to explore that. It's all explained to you, by the way, in the videos, and the sequence is already tell you what to start with. Task 1, task 2, task 3, and there's actually enough details about what you need to change, what you need to keep, and how to run this stuff. Okay, so it's all available for you. Just don't skip. Just do it. Jump whenever you're going to stop somewhere. Watch the video or watch the lecture, the visual lecture videos, and find the answer and continue to do the work. Still have any problem, send me a message. I will contact the person who did that and see what the problem is. Or if I can solve it, I will solve it for you. Okay, I think that actually too much talking maybe is going to confuse you, so I prefer to stop the recording at this point. And